Imagine arriving at a crossroads where a single choice instantly cuts the realm of possibilities exactly in half. Modern machine learning algorithms make life-altering choices on our behalf millions of times a day, but they typically function as impenetrable black boxes, hiding their internal logic from the world. Take the compass algorithm, a tool used by courts in the United States to make parole decisions. Investigations into its predictions revealed hidden biases against certain populations, demonstrating the severe danger of blindly trusting an unexplainable artificial intelligence. In environments where the human consequences are this massive, high accuracy isn't enough. Trust requires a transparent, trackable path of logic. This is where the decision tree algorithm comes in. It operates with an elegant transparency that closely mirrors a game of 20 questions. The algorithm takes a massive, unbroken dataset and begins filtering it downward, routing information through a sequential series of binary, yes or no questions. To see this in action, we can look at a classic historical dataset used to benchmark these models, predicting passenger survival based on demographic traits. By forcing chaotic data through rigid binary gates, the decision tree provides a logical route stretching from the raw input directly to the final conclusion. But with thousands of variables to choose from, how does the machine know exactly which mathematical question to ask first to maximize the effectiveness of the next split? The process begins at a starting root node, containing all the raw, unorganized data points mixed together. To measure this mixture, the algorithm uses a metric called the Gini index. This scores how impure or mixed a group is. A higher number means the data is still heavily entangled. The algorithm scans every available feature, searching for the single split that separates the mixture into two new groups with the lowest possible Gini index. The tree then repeats this exact evaluation at every single subsequent fork in the branch. By mathematically seeking pure, homogeneous groups, the tree autonomously untangles a massive web of data into clear, distinct categories. To see how this looks geometrically, we can map those dots onto a two-dimensional grid. Every time the tree asks a binary question, it mathematically draws a straight, axis-aligned cut entirely across the available space. As the internal nodes continue, they draw perpendicular lines, repeatedly breaking the existing space down into smaller, non-overlapping rectangles. These final boxes are called leaf nodes. Any new data point landing inside one of these boundaries receives the exact same prediction. The algorithm isn't just sorting a list. It is carving a continuous, chaotic landscape into hard territories of certainty. But what happens to this landscape if we never program the algorithm to stop asking questions? The tree enters a failure state, fracturing its clean rectangles into hundreds of jagged, microscopic boxes just to isolate every single outlier in the dataset. This is overfitting. The tree achieves 0% error on its training data by memorizing the noise, making it completely useless for predicting the real world. The engineering fix is to apply strict structural constraints. Setting a maximum depth halts the tree's growth before it can memorize the variations. The most effective model isn't the one that memorizes every irrelevant detail in a dataset. It is the one that knows when to stop looking and draw a generalized conclusion. Even when perfectly tuned, a single decision tree is still structurally fragile. Because it's built sequentially, a faulty split at the top of the root sends every subsequent calculation down an unrecoverable, incorrect path. If a single model is this prone to making a fatal error early in the process, how do we fix it? We gather a whole room full of them.